Hi and welcome to this video, which is about building the process tree. So what is this all about? We know that certain tools like Process Explorer and System Informer, they can show the list of processes on the Windows system in a tree-like structure. We have a tree, or to be more precise, multiple trees of processes representing parent and child relationships. In fact, I talked about that in a previous video or in an older video about why we have that and what that all means, and I'll quickly recap that very soon. And the question is, how do these tools generate that tree? Can we do that ourselves? This is what we're going to attempt to do with some code. So first, let's go back to a tool like Process Explorer and run it and see what it shows us in terms of processes. In fact, the first time you launch Process Explorer for the first time ever, it shows up with a tree-like structure. So here's what we see when we see a list of processes, which is just a flat list. However, we can press this little button shown as process tree, or do a sorting a third time by process name, and we'll see this tree-like view. You notice that we have multiple roots to this tree, so technically we have multiple trees. Here's one root starting with system, here's another one starting with registry, they're all on the same level. WinInit is also its own root, and then there are others that are also left justified beginning their own root, their own tree. Here's WinLogon and Explorer as well. And another way of thinking about it is like just a single tree where we have another hidden node, which is kind of the parent to all these trees or roots that we see here. However, we look at that, it doesn't really matter, but we have this parent and child relationship, which means that if I go ahead and double click one of these processes, I can look at the image tab and see that it was created by this SVC host process with the process ID 1608. And so if I look at the parent, I get that this SVC host is indeed 1608. So that's the right process ID. You can see that here, for example. And it has its own parent, which is services.exe, which is 1464, which is this one right here. So it's about parent and child. I have to be careful here, not say necessarily the creator. In most cases, the creator is also the parent, but in fact, they could be different. A creator can create a process and attach a different parent to it. And so certain properties like a current directory are going to be inherited from that parent rather than the creator. And the hierarchy will show the parent, not the creator. But in most cases, they are one and the same. In any case, some of the processes are left justified. What does that mean? If I double click any one of them, I can see that the parent is a non-existent process which has some ID, which means that the parent ID is stored in the child data structure, but we don't know anything about this process because it doesn't even exist right now, and that's why the process is left justified. So we can try the same trick on other processes. Here's Explorer, for example. We see that Explorer is also parentless. Its parent existed, it had the process ID 5044, but it doesn't exist right now. And you might be wondering, why is Explorer parentless, or why is WinLogon parentless and all that kind of stuff, but this is beyond what I want to cover in this video. There's another hinge here that we have to talk about. We can see here that it says that this is a non-existent process 1380. Now the thing is that when a process terminates and dies completely removed from memory, its process ID can be reused, which means that it's possible there's another process with the process ID 1380, which does exist, but it's not the parent of this one. It just happens to reuse the PID of the parent of WinLogon here as an example. And so what would happen in such a case? Fortunately, Process Explorer doesn't get confused and always checks the creation time if the process ID here happens to exist. And if the creation time of the parent is after the child, obviously that can't be the real parent. So with all that out of the way, we want to build something like that kind of tree. So let's go ahead and start doing that. I'm going to create a new project like I typically do, a simple console application. We can call that process tree. Seems very apt. Let's take the YouTube code folder here and create our project. So we get the initial source file here, just some junk stuff we have from the wizard. I'm going to change that. I'm going to include windows.h so we have access to the Windows API. I also want to use the ToolHelp API, and this is to help me get the list of processes. It's not the only one we can use, but it's fairly convenient and gives us enough information for the purpose of this program. And I'm going to also need a few other things. So first, stdio for using something like printf, but we might need some other stuff as we go along. So how are we going to do all that? So the first thing I want to do is to create a structure to represent information about the process. What kind of data we want to store about the process? So obviously we need first the process ID. We also want to store the parent process ID. We're going to potentially need that in order to figure out whether a process, whether parent of a process is in the system. So we want to keep track of that. We're also going to keep track of the name of the executable or some special name of the process, which will force me to use include for string to get the W string type, the Unicode string type from C++ standard library. And that's what we typically would store for a single process in maybe, I would say, normal circumstances. But in this case, we also need the hierarchy. So every process might have a list of children. So we're going to use a vector here, and I'm going to include vector here so I can get access to that. So I want to keep track of a list of processes. I'm going to use process info as a pointer here because we don't want to store the entire process information. We just want to store a pointer to a process that is stored elsewhere where we have the actual parent, and what we want here is just a list of children. So let's just call that children. So I want to try something like this. And by the way, there's more than one way, of course, to doing what I'm going to try to do here. This is just one way that I hope would work. And if something doesn't work, we'll do some fixes to get it to work, hopefully. And so as we've seen in Process Explorer, we have a list of roots. So let's just store these roots here. So let's call that let's call it roots. Why not? Seems like a good idea. So I'm going to have a roots of process info. These are the actual structures. But since we're going to deal with pointers also, and with vector, when we add items to the vector might need to resize itself. So process info objects might move around in memory. So it's going to be tricky to keep track of pointers in a safe way. So I'm going to use a unique pointer here. I'm going to basically store pointers that are managed by unique pointers so that when it goes out of scope, at the end of the scope of this variable, the entire memory is going to be automatically freed. So I don't need to do something like new and delete. I don't have to do that. Unique pointer is going to deal with that. Unique pointer just means there is a single owner to that object of type process info. And we'll see that hopefully this will serve us in a good way. Another thing I might want to keep, you know what, let's just start writing and see if we need anything else from that. So the first thing I need to do is to get a snapshot of all the processes in the system. Like I said, I'm going to use the ToolHelp API, an API that I already demonstrated in an old video. You can dig that up if you wish. So I'm going to use snap process here. That's the flag to get all the processes in the system. And technically, this has to work. If it fails, that means we're completely out of memory. So that's really bad, but unlikely to happen. But just let's check it for good measure. And then we can start doing the iteration. And this is done using the structure called process entry 32. We need to initialize the size to the size of the structure. So let's do that. And then we can start the iteration. And the first call is process 32 first. That's the first thing we need to call in order to get information about the first process. And then for subsequent processes, we're going to use the function process 32 next. So technically, we're going to use that process and do something with it. We can continue this loop while process 32 next is going to return us true, which means there are more processes in the list. So we need to deal with that process entry right here. So what are we going to do here? First, we want to build a process infrastructure representing this process. Obviously, we need something like that. And this is something we want to keep track of. Otherwise, it would be very difficult for us to actually do something with that. And so we can create that process info. Since we're going to use the idea of a unique pointer to store that, we can create that using the function makeUnique, which basically by default just uses new behind the scenes to create a process infrastructure instance right here, and just gives me back the unique pointer, which means the memory is self-managed, which means that when the object goes out of scope, the memory is going to be freed automatically without me having to worry about it. And so we have our pointer here. This is a smart pointer, so it's an object that is the unique pointer, but behind the scenes there's the actual object, and we have, since it's a smart pointer, the class provides an overloading operator for the error operator, so we can get to the actual object beneath without having to do much juggling in terms of coding. So we need the process ID first, so let's go ahead and put it using PE, that structure of process info. So we have the structure here for the process ID, here goes. We also have the parent process ID, so let's grab it as well. So here's a parent process ID, and there's also the name that we want. So let's grab that as well. It's called SZEXE file. And then we have children, but at this point we don't know which children are children of this process at this point, so there's nothing special to do. We want to add it to somewhere. So where are we going to add it? Well, we need to look at the existing processes and see whether the parent actually exists. If it does exist, we're going to have to add it to the parent. If not, it's going to be part of a new root. And so how do we check that? We need to know whether we have already encountered this process with this ID. So for that, I'm going to add another data structure. Technically, we could move this a little bit further down. I'm going to add a map that can find quickly the existence of some process ID based on the type of D word, and then give me back the pointer to that process. So we can call that map or whatever. So I'm using unordered map here, which is one option. So I'm going to have to include that. You can also use the classic map, which is also fine. In this case, it doesn't really matter that much. It's just a different algorithm used behind the scenes. Unordered map is a hash table, and map is a self-balancing binary tree, if you care about these things. In any case, we have that, and technically we could have used just another vector and just do a linear search, but this is just going to be technically faster, especially if there are many processes in the system. So I'm going to do a check. So I'm going to search for my process here. So I'm going to use the find method on the unordered map and look for the process ID. See if we've seen that already. If we have seen that, which means there is a parent there, so we need to look at the iterator. If it's not end, it means that there is something here, and we want to add that as a child to that something, because that something already exists. So we want to add that, the current process, to that parent. Oh, sorry, we're looking for not the ID, but actually the parent ID. This is what we need. And of course I have a silly error here. So parent ID, obviously. So I'm going to look for the parent ID. If it exists, we want to add it to the child. If it doesn't exist, it means it's a process without a parent. And this means that it has to be a root process. So we're just going to do roots and add that to the list of roots, the list of root processes. So I'm going to add PI here like so. Well, almost. Since we working with a unique pointer, we have to move it so that the ownership is transferred to the vector, the roots vector here. You can also see Visual Studio is not very happy about the code I've written here, and this is simply because this idea of using initializer and then as part of an if statement is actually a C++ 17 feature, and by default Visual Studio 2022 uses C++ 14, so we need to do something about that. I'm going to just go to the properties and change the standard to C++ 17 or 20, it doesn't really matter, but at least 17 so that the compiler is happy and now Visual Studio is happy. So if we found the parent ID, we can go ahead and look at the second. That's going to be the actual value. So we have a key and value there. First is the key, which is the process ID of the parent, and second is the actual process ID. And so we have the children here. We can now add this as a child. So we can just go ahead and add the pointer to the list of children, because it means that we technically have a parent, so we just need to add a child to it. So technically what I've done here is not good enough. I need to actually store unique pointers as well here so that we can keep the memory working correctly and just being freed at the right time. So I need to push back here and just move the process information, the process info object into that container. And basically we're done. Well, we're almost done, not truly done, but we're kind of done in the sense that we're going over all the processes. If we find the parent, we add it to the parent. If we don't find the parent, we just make it yet another root. Now, one thing here that we're missing is that maybe the process ID exists, but of the parent, but it's not the real parent. Because of process ID reuse, it's actually a different process which is completely unrelated, and it's not really supposed to be the parent, so we should do an extra check here. But before we get to that, let's see if this works in some way. So I'm going to close the handle for the snapshot just to be nice, and I want to have a function called displayTree that's going to receive the list of roots. So we're going to pass roots here. That's the list of roots, and this is supposed to display the tree. If it does that, then we know that we're on the right track, and we'll just have another thing to handle here. So let's write displayTree. So what is that going to look like? So we have displayTree, and it's going to get the vector of the roots, which means we have a unique pointer here. So obviously I'm typing a lot here with this std : so let's just do something to remove that. I'm going to just switch all of them out and just delete all of them, and use here using a namespace std to make things look a bit easier on the eyes. So now we have that, and that's better, I think. So I'm going to have a reference, a const reference to this vector. I just need to get that reference to work with these roots. Let's call it roots, just to be clear. So the rest of the code didn't really change. It all should be still fine. We just not we have not implemented this function just yet. And what we want to do, we want to display the list of processes, but we want to display them in a tree-like manner, which means that we also need to do some indentation when we reach child processes. And so how are we going to handle that? So what we're going to do, we're going to add another parameter here. Let's call that indent and give it a value of 0 as a default. Since we have that 0 as a default, that's what's going to be passed here in display roots. So display roots the call here to display roots doesn't need to know, to display tree, sorry, it doesn't need to know anything about the indentation, but every time we perform this call again, because recursion is going to happen here, we're going to increment indent every time we deal with children. All right, so now we can get going. So the first thing we're going to do is iterate over the roots here. So I'm going to get each one of these in place. So the first thing I want to do is to display the current process and then display all the children of the current process recursively. The power of recursion is amazing. I think recursion is one of the best things we have in programming. It can help us solve seemingly difficult problems relatively easily once you get the hang of it. So I want to display the process name and the process ID or something like that. So let's go ahead and do that. So here's the process name going to be, let's use WS here. And we want the process ID here like so, something like that. But before we do that, we actually also have to display, well, let's just fill in that for now. So let's start with name. So we have a W string here, so we need the CSTR, the actual pointer, because that's what %WS is expecting. And then we have the process ID, of course, we can just grab that. So we have that and we have displayed it, and we can definitely go to the next line. Sorry, name is just a variable, but we want to first display number of spaces, which is based on the indentation. So we need to have another printf here. We can do that in the same line, but just to make it clear, I'm going to do that on a separate line. And one of the things that we have in the string class, we have a constructor that can do exactly that, essentially duplicate a certain character so and so number of times. So in that number of times, we need this just a space. So just give me number of spaces, which is based around the value of indent, which of course is going to start out at 0, which is fine. But then once we've displayed the current process, we can go to display tree again. We're going to call that recursively with the children of this current process. And of course, we're going to increment the indent. Now, of course, the children could be an empty vector, which means nothing interesting is going to happen. And technically, we can slightly optimize that by checking first that children is not empty. Otherwise, it's going to be kind of a useless call to the recursive display tree function. It's not going to do anything. But the important point is to increment indent. So now we're going to pass that with a value of 1. And then if that process also has children, it's going to pass the recursive call with a value of 2 and so on. When we go back out of the recursion, then the previous indent, of course, is going to be maintained because we have a new stack frame. And then once we go back, it's the old stack frame and the same value for variables. And that's basically should be it. Okay, time to test it without the last step that we're missing. But let's start with that. Okay, so I'm going to press Ctrl F5 to run this. So here's what we get. Well, not quite what we expected. Definitely not good. And maybe you've noticed the bug here. So although I've did these checks and that's nice, I actually didn't add any information to the map. So the map was always empty, which means it would never have identified any parent processes or any process whatsoever. So that's not going to work out. It's not going to be good for us. So we need to insert the process to the map so we can keep track of all the processes in the system. So we can do the find here next time in this iteration. So technically we should go with PI and then take the ID like that, and then PI itself with the pointer, but that's not going to work out well. And you can see that, well, actually I just called the function incorrectly. We need to provide a pair, so that's the easiest way to do that. So now the compiler is going to be happy enough, but actually what I'm doing here is wrong. And it's wrong because of the move operation for PI, which actually moves the ownership from this local variable, which now becomes empty, to either the children here or to the roots. So in either case, a map here is going to be actually junk, so it's not a good idea to do that here. And so we can do that before, like here, that's going to be fine. Or we can just keep the pointer and then just save the pointer in local variable and then use that pointer later. But that's going to be good enough, I hope. Let's try this again. So now here goes, and you see that now we get some different output, much better in fact. So you can see CSRSS, WinInit, and services. We can see they're part of a tree. So WinInit is a parent of services. Services is parent of this SVC host. SVC host is parent of WMIPRVSE, and so on. At some point you might see processes which are completely left justified, which don't have a parent, like this CSRSS here, and we log on here and explore that we've seen also in Process Explorer. So it looks like we're doing the right thing. It looks very similar to Process Explorer, maybe not quite exactly like Process Explorer. For example, something seems to be missing, like what about secure system? What about registry? What about the system idle process? Some things seem to be missing here. And you might be able to guess why these processes are missing. And if you're thinking security, then you're right. And Process Explorer here is running with admin privileges, so it has access to all the processes. But since my application here is not using admin privileges, then certain processes that are very well protected are not provided to me in the enumeration properly. So we can go ahead and restart that as admin. So I'm going to just simply cheat here and start with the processes, the Visual Studio as admin, and run things as admin, or I could just leave these things as they are and say, you know what, that's the part that I have right now. But just so we can have a better comparison with Process Explorer, let's just run that with admin privileges. I'm going to press Ctrl F5 again and see if we get something different. As you can see, it doesn't seem that I'm getting something different here, which is kind of weird. So let's continue seeing what's going on. Maybe I actually have a bug here. Maybe it's not about security at all. Maybe it's about a bug that I have in the application. So we have the process here. We're inserting that into the map, and then we're searching for the parent ID. If we find it, then we just add the child to the list of children. Otherwise, we're adding that to the root. So that seems to be pretty good. Okay, time to do some debugging. Let's go ahead and see what is going on here. Let's put a breakpoint here and see what happens. So we have the process ID of 0, which is the first one. That's the system idle process, and we insert that into the map. But now we're looking for the parent ID, but the parent ID is also 0. So we find it and we add it to process ID 0, which doesn't really make any sense because it doesn't really, it's not its own parent. So technically we want to make the insert later. We actually want to put the insert later after we're doing these checks, and then see if it actually makes any sense. It means that the process 0 is not going to find any parent and it's going to become a root, which is what actually should happen. And so we have to go with my previous idea that we have to grab the pointer before we're doing the move into either the map or, either one of the children or the root, so we can properly get to the object. Just to prove what I'm talking about, let's go ahead and press F5 here again, just to, if you haven't done these kinds of things in C++, it might be a bit confusing. So you notice that PI here is actually empty. There's nothing here. It's pointing to nowhere. That's because the ownership of this object has moved into this or into that. In this case, it's moved into the root because there were no processes at the time. So using PI here is actually bad. So what we're going to do is simply using P here. And in fact, you can see that you get these squiggly sometimes, indicating that the IntelliSense already knows something is fishy here. It knows it must be empty because it has been moved for sure by one of these instructions. So I'm just keeping the pointer here. We just need the pointer, and then we can go ahead and insert that into the map. Okay, so now let's be optimistic and press Ctrl F5 to run this thing. And here goes. Okay, so now it looks much better. We have the first process. It's called system process, actually, the system idle process, because this process doesn't really have a name. So every API gives its own name, and the ToolHelp API calls it system process in square brackets. As you can see, there's actually the system process called really system that has a PID of 4. So now you can see secure system, registry, SMSS, memory compression, all this kind of good stuff. Something similar to what we see in Process Explorer. In fact, Process Explorer is a little bit buggy there. It doesn't show things quite right for the first few processes. Anyway, I'm not going to deal with that. So the last thing we need to do here, just to make sure we're really covered, before we decide that this thing is actually the parent, we have to verify that it is in fact the parent. And the way to do that is to check the start time of the parent compared to the child. So we can say start parent, let's call a function called get start time, and we'll pass the process ID for the parent. And then we'll also take a look at the start of the child, that's the current process, by calling the same function, which we have yet to write, and just look at the process ID here. And we can say if start parent is not 0, and we're going to use 0 here as a way to indicate a failure. So if start parent is not 0 and start child is also not 0, which means we managed to get some start time, and start parent is less than start child, then this is a true parent, and we actually do have to add it here into the list of children. Otherwise, it happens to be something else, which is not a real child, which means that it's just a reused ID that happened to have the same ID of some parent process. In this case, we have to add that as a root. So we have to change the logic here a little bit. So we can say bool root, let's call that true. And then if you do get to this location, we can say root equals false. And now we're not going to have an else here. We're going to say if it is a root, then we're going to add it to the list of roots. So that's what we're going to do. We have to have that extra stuff in case we have a reused process ID. So we need to get the start time of a process in general. So we have to have another function here. Let's call that, we call that get start time. We need to provide the process ID, whatever that process ID is. We need to return some value. So I'm going to return an unlong ulong 64, which is basically what we're going to get, a 64-bit value, which represents the start time of a process. The actual units don't really matter, but they're going to be units that are 100 nanosecond units from January 1st, 1601. Yes, I know it's crazy, but if you're familiar with Windows, this is something that shouldn't be a big surprise there. But it doesn't matter, we just care about which one is greater. We don't care about the actual units, although we just need to make sure they're the same units. We're going to use the same APIs, so it's going to be the same units. So how do we get to that information? Well, unfortunately, since we're using this particular API, the tool snapshot, this API doesn't provide the start time out of the box. We have to work to get it by using the open process function, which sometimes can fail. For certain processes, it might fail, which means that in this case, we're going to return 0 as a way to indicate that we just don't know. But for most processes, this should work. We need to get the process handle with the process query limited information. That's enough, which is a very superficial way of getting information from a process, and that's why it works for most processes. So we have the ID here, and we can say that if this doesn't work, which means we get a null handle, we're going to return 0 to indicate that we just don't know. In this case, we're going to just believe whatever PID for the parent that we have, and we're going to assume it's a parent, and that is it. We also need to, well, I think that's good enough for now. So the next thing we need to do, of course, is to call some function to give us the start time. I'm going to use the function getProcessTimes. GetProcessTime actually returns multiple times. It gets the creation time, the exit time of the process exited, the kernel time, and the user time. So different things. We're not interested in anything except the start time, but unfortunately we still have to provide all of them. So we have the create time, let's call that start, just for consistency. And then we have some other parameters which we have to specify, unfortunately. We can't specify null. In this case, the function will simply fail. So we have to specify something. We're just not going to care about what we have there. As you can see in the parameters, what they want is a file time thing. A file time is just a 64-bit value that is comprised of two 32-bit values, which is also used for file times, as the name suggests. But in this case, it's used for something different, but still the same units and the same general idea. So the creation time is the first parameter here after the handle to the process. I'm going to give it a nice name, and then the others are going to just be dummies that don't care what is in there. So if that works, well, we can say that if, well, let's go ahead and get that as the time. well, the time is actually inside start. We just need to know if this succeeds or not. So obviously it must succeed if we get a handle, so I'm not going to check that. I'm just going to return the value. Before I do that, I'm going to close the handle to the process to be nice, and just return whatever we have in start. But because start is a file time, which is kind of annoying, I'm going to have to do some casting here to look at that as a 64-bit value, like so. And now we're really done, so I hope. So first, let's go ahead and see if our logic here that we've changed doesn't have any bugs, because it definitely could have bugs. And we get here something which is probably going to be very similar or probably identical to what we've seen previously, simply because the chance of having an ID reused is not that great. It could happen, definitely, but it's not something we might see very often. So it's really difficult in this case to say whether we've actually avoided that particular problem without doing any extra investigation to see whether we actually do have a duplication here. So there you have it. This is how we can create a process. This is basically what the tools are doing. They might use some different way to store the information. That's really up to them, but they're doing something similar to figure out which process is a parent, and if this is the case, they attach a child to it. I definitely recommend you try it yourself and maybe play with that in various ways to see what you can come up with.